Hello and welcome back to Real Analysis. And as always, many thanks to all the nice people that support this channel on Steady or PayPal. In today's part 20, we will talk about two important criteria we have for the convergence or the divergence of a series. They are simply called the ratio test and the root test. In the best case scenario, they answer the question if a given series is absolutely convergent. Here, please recall, we have already learned in the last video, if we have a convergent major end, the series is absolutely convergent. This is known as the comparison test. The only problem here is that we really have to find such a major end. Therefore, we might try to use some series where we already know that they are convergent. For example, we already know the famous geometric series. As a reminder, let's state the fact again which holds for the geometric series. We know that summing up the powers of q gives us a convergent series if and only if this q is in the absolute value less than 1. We need this fact for real numbers q, but I can tell you it also holds for complex numbers q. This is good to know in the case that you also watch my complex analysis course. Okay, now here we will apply the comparison test by using the geometric series. And let's put all of this into a proposition. So if we find an index n0 and a number q which is in the absolute value less than 1, and with the property that the absolute value of ak is less than q to the power k, for all k greater or equal than n0, then the series ak is absolutely convergent. This is simply the major end criterion from the last video. And we just use the convergent geometric series for the major end. Okay, we can change it a little bit because we don't destroy the convergence when we multiply the series with a constant. Therefore, we can simply introduce a constant capital C here and we have the same result. Now again, this is simply the major end criterion, which might be helpful if you want to check for convergence. Still here, you have to find a suitable q such that this inequality is fulfilled. Therefore, it might be psychologically helpful to rewrite the whole thing. And one possibility leads us to something we call the ratio test. There, we just have to calculate a quotient. Namely, we just take ak plus 1 and divide it by ak. And if this is measured with the absolute value less or equal than q for all k, then the series is absolutely convergent. For some examples, this can be very helpful when you can calculate this fraction, or when you can estimate it very easily. Of course, for the correct formulation here, we have to choose our n0 again and the number q. In order to make this formulation simpler, we can just choose q between 0 and 1. Because obviously a negative q won't work here. However, please keep in mind 1 is excluded here. Okay, so we want this inequality here eventually, so for all k greater or equal than n0. However, we can only have that if the denominator here is always non-zero. Hence, to be correct, we have to include this information here as well. Now, before we do an example, let me show you the proof of the ratio test, which is very short. Indeed, we have already all the information we need. In the first step, let's multiply this inequality with the denominator. Then we get this nice inequality, which holds for all k greater or equal than n0. This means we can apply it again on the right hand side where we have the absolute value of ak. In other words, we have here q times ak minus 1. And then we can do this again and again until this index here is n0. I just say you can do this inductively because the formal proof would be a proof by induction. Okay, and here we just have to count how many steps we have, so how many factors q we have. And it turns out we have k plus 1 minus n0. Of course, we can just rewrite this if you want with the correct factor k plus 1. Simply by dividing with q to the power n0. There you see, both things together gives us this power back. We do this because now this whole inequality, left hand side and right hand side, is of this form here, where our constant c is simply this fraction here. However, this whole thing now means that all the requirements of the majorant criterion are satisfied. Hence we can conclude that the series is absolutely convergent and we have proven the ratio test. Okay, so now let's demonstrate how helpful this test can be with an example. Here let's consider the series with 1 over k factorial. The question for you is now, is this a convergent series? Now because there is a fraction involved, maybe the ratio test gives immediately an answer. Therefore I would say, just let's calculate this fraction here. We just have positive numbers, therefore we can omit the absolute values. Okay, so this is the fraction and now we can use that we know what k plus 1 factorial is. It is simply k factorial multiplied with k plus 1. This means that everything cancels out here except one factor k plus 1. And the crucial thing here is it's in the denominator. Therefore we immediately see this is always less or equal than 1/2. Hence this 1/2 is our q and n0 we can choose as 1. Of course, if you would choose a larger n0, you could choose a smaller q. However, this is not important. The important thing is that you can choose q less than 1. And of course, 1/2 is a good choice here. Okay, and there you see, we are already finished. The series is convergent. Now, before we go to the next test, I should warn you that you really should be careful in your calculations. If you just show that this fraction is strictly less than 1, this is not enough. Of course, it looks similar to the inequality we want, but please note it's not the same. And also, you already know a good example for this. Namely the harmonic series, which is divergent. Okay, with this in mind, let's go to another important test, the root test. As the name suggests, here we don't look at the ratio as before, but at a root. More concretely, we will look at the kth root of a k in the absolute value. And as before, this should be less or equal than a given q. And the overall assumptions for q are of course the same as before. And then we can conclude that the series is absolutely convergent. Here you see, unlike the ratio test, the root test does not need that a k is non-zero. In this sense, we have fewer assumptions here. Okay, then let's write down the proof, but I can tell you it's probably the simplest proof we have ever done in this course. Because in this inequality, we can simply use the kth power on both sides. And then we simply have that q to the power k is a majorand for ak. Or in other words, we have the geometric series as a convergent series in our comparison test. And this immediately gives us that the series is absolutely convergent. Therefore, one could say the root test is exactly the same as the comparison test with the geometric series. Still, this formulation might be easier for you because you have something you can calculate. Let's simply demonstrate that with an example. So here we have a maybe complicated looking series, but there's a power involved. Hence the root test could be suitable to answer the question if this series is convergent. So for the coefficient we take the kth root. Then the power cancels out and only the power 2 remains. Hence we only have the fraction 9 over 2 plus k, which is less or equal than 9 over 10. Of course, this only holds for k that are greater or equal than 8. In summary, there we have our n0 and there we have our q that is less than 1. Therefore we can conclude this series is indeed convergent, namely by our root test. Okay, so this was an example how you can apply this nice criterion. However, we can make it even better by avoiding that we have to choose q and n0 in the end. Indeed, this works because we can reformulate the whole statement with the limit superior. In fact, this is what you should remember. You can calculate the limit superior of the kth root of ak. And if the result is strictly less than 1, our root test is fulfilled. In other words, all the requirements are fulfilled and we can conclude that the series is absolutely convergent. In our example from before, we just have to look at the limit superior of this result here, which is in this case simply 0. Hence I think this is very helpful, psychologically helpful, because you don't have to guess a suitable q. You simply get a number out and you can check if this is less than 1. Also, what one can prove is that it works the other way around. Meaning if the lim sub we calculate is strictly greater than 1, then the corresponding series is divergent. This also follows from the comparison test with the geometric series, but now with the minor rank criterion. Okay, so please remember the whole thing here for the root test. And please also remember, if it happens that you get out 1 for the lim sub, we are not able to say what happens for the series. Indeed, 3 cases are possible then. The first case would be the series is divergent, and the second case would be it's absolutely convergent. And the third case would be it's neither of them, it's just convergent. Okay, I think that's good enough for today. In the next video we'll still talk about series and I hope I see you there. Have a nice day. Bye.